Okay, so now in this video we're going to talk about the simple pendulum and the sinusoidal nature of a simple harmonic motion, right? So let's make a title here. Simple pendulum. First thing, so we can actually define simple pendulum motion for any object, right, which is having a restoring force. So you can say that a simple pendulum is actually a simple pendulum when you have a restoring force, right? You have a restoring force which is exactly equals to the negative of the displacement. Restoring force is equal to the negative of displacement. So if we draw it out our simple pendulum here on this side, so let's say this is the solid rigid support, you have a pendulum string and it is swinging, let's say length, let's say it is swinging, and that's the pendulum right there. We have, let's see, draw it again. That's the pendulum, that's a swinging. This is the bob which is attached at the end, and the bob is experiencing the force of tension in the up direction as a F suffix T. If I say, if that's the angle theta, the length of the pendulum is of course as L, right? That's the length. So this experiences a force of gravity in the down direction. It has a two component of force of gravity. One is mg right here. That's the actual force mg, but at a component you have two component. One is along the axis, that way we can call this as a mg cosine theta, okay, and the one which is along the this direction, which we call it as mg sine theta. So that mg sine theta is actually a restoring force because the pendulum is on a end of a swing. It wants to go back to its original position, hence that is considered as your restoring force. Now this is the length, okay, how far it went from its equilibrium position, length x, you can call, and it's going to go swing back and forth like that. So I'm going to draw with another color just to show you that it's swinging back and forth like that, right? So long story short, we can say that the restoring force for this pendulum of f of x is just negative mg sine theta. In the opposite direction the restoring force is. You can consider this simple pendulum as a simple if your angle is less than 15 degree, and because it is less than 15 degree, then we can say that your sine theta is close to theta, okay? Again, this is for the small angle approximation that we are using it, okay? This x, which is the distance it is traveled in the horizontal direction, we can consider that using a Pythagorean theorem as a L times theta, right? Because it's adjacent opposite side of it, so you can do L over theta. And if that's the case, in our force equation, force F equals to mg sine theta, I can write mg as just theta because the sine theta is very near to theta as a small angle approximation. Put the value of theta as minus mg, theta is L over x, theta is x over L, I mean to say, x over L. And that's how we got our f of x. Now f of x for any scenario, it is going to be, you know, if we learn in our spring constant, f of x is just negative kx, which is equals to negative mgx over L. So for the simple pendulum, the constant, like in a spring we have spring constant k. For simple pendulum, the spring constant k for simple pendulum is k equals to mg over L. Now you say, Mr. Shah, why and how this is helpful? Well, look, we know from mass spring system, the period is t equals to 2 pi under root m over k. We can put the value of k as mg over L in that equation, and now we get the period for the simple pendulum. M instead of k, we can put mg over L, so m can cancel out, and now you have a period equation for the simple pendulum, which is just L over g. See, That is only for a simple pendulum. You can write the frequency equation as 1 over 2 pi, okay, G over L. This is the period and frequency equation for simple pendulum. So as you know, that simple pendulum does not depend on what you are hanging. It just depends on how long the pendulum is. Okay, with that, we're going to try another thing which we want to do, which is sinusoidal nature of wave. So let's talk about that. Sinusoidal nature of simple harmonic motion. So as we know that when we apply a higher amount of math into our simple equation, which is F equals to negative kx, you can write F equals to ma, and a is your d square x over dt square from a differential equation, what we have learned previously. So we can actually write that your d square x over dt square for a simple Hooke's law can be considered as a negative k over mx. This is a second order differential equation. So if there is a question asking you that, hey, can you derive a second order differential equation for the simple harmonic motion, this would be your second order differential equation. Differential equation for simple harmonic motion. Correct? Let's call this equation as 1. And if we say now in general, the above equation, you can be proved using a trig function, right? If you want to prove this using a trig function, you can say, hey, if a simple pendulum is going, or simple harmonic motion for a position of any time given at any given time x, you can write as a cosine function a cosine omega t plus phi, where omega is angular frequency, a is amplitude. That's right, a is amplitude, your t is a time, right? Your phi is a phase angle, right? Your phi is a phase angle or phase constant, phase angle or a phase constant. And your omega is your angular frequency. So with this equation, if I differentiate with respect to time t, if I do d dt of this xt, you know that the cos will become negative sine, and your omega t is differentiated, so it will become negative a omega sine omega t plus phi, right? So if I rewrite it again here, this is a little bit crowded here. So we can have a d of dx, which is a t, which is nothing but just a velocity, which is a velocity. Velocity dx dt equals to negative a omega sine omega t plus phi. If I do differentiate second time, I'll get d squared x over dt squared. Second time differentiation, sine become cos, omega t become omega, so you will have negative a omega square cos omega t plus phi. You see, you get the same equation again, right? A cos omega t plus phi we started with, and we end up with the same equation. So we can say this, that d squared x over dt square is nothing but negative omega square times x, because x is a cos omega t plus phi. So look, we can compare equation number 1 and equation number 2. Can we compare equation number 1 and equation number 2? Yes, we can. Let's see, compare 1 and 2. If we do that, we get negative omega squared x, which is nothing but negative km over x, which is telling you that omega is nothing but square root of k over m. We give you relationship between the angular frequency, spring constant k with the m, right? So this shows that the simple harmonic motion is a sinusoidal wave. sinusoidal wave function with the omega is the angular frequency, with the omega is the angular frequency, with the omega is the angular frequency of that oscillator. Now remember, I use the word oscillator because it is oscillating back and forth with the same amount of time, right? So we can show you that your position versus time graph for this oscillator, because it is going a cos omega t, it's going to start from right here somewhere, going back and forth like this for x. Again, this is giving you relationship as x equals to a cos omega t plus phi. Now look, if I put omega equals to square root of k over m, let's see what happens. A cos, instead of this, I could put square root of k over m t plus 5. Let's see what happens. We can say omega, nothing but 2 pi over t. You know, omega is 2 pi over t, which is coming out as a square root of k over m. Boom, you got the relationship for that as a t equals to 2 pi square root m over k. We proved it again that the period equation is a 2 pi m over k once again. Right? We proved it once again. T equals to 2 pi m over k. Now, with this, we can define a velocity equation with the same relationship too if we do a velocity versus time graph. Now, you know velocity versus time graph is a sine function, so it has to start from 0 and going up and down with the time t, because your v is nothing but dx dt, which is nothing but negative a omega sine omega t plus phi. Okay, same thing we can do with the acceleration, just trying to show you the relationship between position, velocity, acceleration with respect to time t. T is again starting out as a negative a omega square, right? It's a square function, so it's going to go all the way down, right here. It's going to go up and come up, go up, come up, and we will have the all three things at the same time, where you have acceleration is a dv dt, and we differentiate again one more time. We got negative omega square cos omega t plus phi. Remember, it's a cos function, that's why it's not starting from 0. Okay, so that would be it for this video. We have covered two things: simple pendulum and sinusoidal nature of a simple harmonic motion. Thank you guys.